All right, welcome back, Stats. We're on 6.4. This actually is not in the book, so I do have a PDF file on Schoology. Alternatively, you could just keep taking notes in your notebook, however you want to do it. But we're going to talk about the geometric distribution. So, suppose you are throwing darts at a target, and the probability of you hitting the target is 0.17 or 17%. What's the probability that it will take you exactly 8 throws to first hit the target? So what we want to notice here is that it's slightly different than a binomial distribution. It's still that type of success or failure, right? Two outcomes, either hit or miss. However, the question part of this is a little different because it's asking what's the probability that it will take you a certain amount of trials, right? So we don't know how many trials it will take, but we're asking, what's the probability that it'll take a certain amount of trials in order to get your first success, okay? So in this case, the first hit. And that's what a geometric distribution looks like, okay? Or that's when we would use a geometric distribution. So there are one or more trials with all failures except the last one, right? So it's, in this example, it would be like miss, 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 and then hit. And then we would stop there, right? The probability of success or failure does not change from trial to trial, so it's the same. And technically, there could be an infinite amount of trials, right? So if our probability is really, really, really low, and you just kind of had to keep going. Like, so if I told you, I was thinking of a number between 1 and 20 billion, and I said, okay, try and guess the number, and keep guessing until you get it, that's going to take a long time, right? So, anyways, let's take a look at, do something real quick here. Take a look at this example. So we need, in order to answer this question of exactly 8 throws in order to get our first hit, we would need the first 7 throws to be failures, right? We would need those first 7 to be misses, and then the 8th one to be a make or a hit. So what is the probability that the first throw misses the target? So in this example, we're talking about the probability of success was 0.17, right? So what's Q? What's the probability that we miss? Well, that would be 83%, right? The other probability, 1 minus 0.17. So the probability that the first throw misses the target is 83%. What's the probability that the first and second throws miss the target? Well, for that, the probability of the first one missing the target is 83%, right? And these are all independent events, so the probability of missing the second one is still 83%. And because these are independent events, we can just multiply, right? And so what is 0.83 times 0.83? We get about 68.9%. So about 68.9%. Okay? What's the probability that the first 7 throws all miss the target? Well, okay, wouldn't that just be 0.83 times 0.83 times 0.83, or what's the, I would keep going until there's 7 of them, or what's the easier way to write this? 0.83 raised to the 7. And so let's see what we get here. 0.83 raised to the 7 would be about 27.1%. So the probability that the first 7 throws are all misses is approximately 27.1%. What's the probability that the 8th throw hits the target? Again, independent events, so it doesn't matter what happened before. The probability on that 8th throw of hitting the target is 17%. Okay, now let's put all that together. What's the probability of the first 7 throws all miss the target and the 8th throw hits the target? Well, we would have both of these things that we just did kind of put together. And so we would have the idea like that, right? And we would just multiply these two things together. I already have this 20%, 27.1% on my calculator, so I'll just multiply that by 0.17, and I get approximately 4.6%. And so that is the probability that it would take us exactly 8 throws to hit the target for the first time. Okay? And that is a geometric distribution. So using this idea, right, to find the probability that x is equal to some number, let's call it k. Okay, to do that, what we would do is, well, because it's geometric distribution, the last one has to be a hit, so it's going to be the probability of success times the probability of failure, and that's going to be raised to 1 less than the number we're looking at. Okay? So we have our probability of success. We have our probability of failure. And the exponent on that is 1 less than the sort of x value we're looking at. So it's less than the x value in the question part of it. Okay, so suppose you roll a regular 6-sided die. How many times does it take to first roll a 6? So first, what would you guess for that answer, right? Obviously, this was designed to be notes that were a little different. We're supposed to be in class. Some might say, okay, maybe 6. Some might guess 3. Some guess 4 or 5. Who knows? Okay. The problem is slightly different, but it's not really. The difference is that we're not exactly saying. We're not given an x value. We're not saying what's the probability that it will take a certain amount of rolls. We're asking how many rolls will it take, and this is actually getting at the average of a geometric distribution. And so the average of a geometric distribution is 1 over p. So, for example, in this idea, if you guessed 6, because there's 6 outcomes, and so it's like, yeah, you probably will need 6 to get it. That's the average. So the idea here is that the probability of rolling a 6 is 1/6. And so this average of 1 over 1/6, 1 divided by 1/6 equal to 6, right? Or just reciprocate it. If we're given the previous example of 17%, if I wanted to know the average of that geometric distribution, what I would do is I would do 1 over 0.17. And so I'd have an average of about 5.88 throws, right? So on average, I would need to throw the darts about 5.88 times in order to hit the target first. That's the idea of the average of a geometric distribution. Okay? Again, the next part is just talking about, we've talked about this before. This is the difference between theoretical and practical. Right? If I'm telling you that the average amount of times you would have to roll a die to get a 6 is 6 times, that doesn't mean that every single time it's going to take you 6 times. It's an average. It's a theoretical average. In practice, practical terms, you might roll the 6 on the first throw. Or it might take you like 20 throws to get a 6. Who knows? Right? It's the difference. However, this idea, which is huge in statistics, is that if we keep increasing the amount of trials, right, as the number of trials increases, what's going to happen? The number of trials increases, right? If it took you 20 throws, but it took somebody else 2, well, now we got a different average, right? Now we're averaging 11 throws. And when we add more and more people in, and we average all of them together, as the number of those trials increases, the practical probability approaches the theoretical probability. And there's an idea we've talked about before. If I just throw a die and roll it until I get a 6, it might take me, let's say, 12 throws because I was unlucky, right? But if I keep doing that over and over and over again and average all those numbers together, it's going to get closer and closer and closer to 6 because that's the theoretical probability. Okay? So, I need more room. All right, let's bring this back up. Okay, so let's do an example here. I didn't have an example on that sheet. So, don't know why this isn't working. There it goes. So let's do an example here for this geometric distribution. Let's say that we are testing product deficiencies. Why didn't I pick a word I could spell? Deficiencies. I think that works. Maybe. So we're testing product deficiencies. So defective products. So let's say the rate of defective products is 0.1%. Okay, so 0.1% defective rate of products. We're going to test products, and we want to know, what's the probability it will take, how about 45, that's pretty low, hold on. How about it will take, let's say 95, it's not much better. Probability it will take 95 tests to find the first, that says first defective product. Okay, so this is an example of how we would use this. So what's the probability to take 95 tests to find the first defective product? Well, this is an example of geometric PDF. We don't really have to use that formula we came up with. We could certainly use that formula we came up with, but the calculator can do it for us. So if we go to our distributions, we find geometric PDF at the bottom. We hit enter. It's asking us for the probability. And so in this case, it's that last probability, the probability of success, which in this case is finding a defective product. And so that is 0.1%. Remember, we have to convert that to a decimal. So that's actually 0.001. Okay? And we're wondering, what's the probability that on exactly the 95th, what's the probability that we're going to get our first defective product? And this is not going to be a very good example because we're going to get probably this really, really low number. Yes. So we got 9.1 times 10 to the negative 4. So we're getting a very, very small number here, right? So this is a geometric PDF of 0.001 and 95. And it's very small because the probability of getting it exactly on the 95th is very low, and it's almost equivalent to 0%. It's not exactly, right? There's a slight chance, but it's very close. If based on our rounding methods, it rounds to 0%. Okay. What's the probability that it would be less than or equal to 95 tests? So in this case, we would be using, so how about less than or equal to 95? So in this case, we'd be using geometric CDF. And again, I don't think my example might not be the best. And we're going to get, so now this would be anything up from 1 all the way up to 95. So it should be a larger probability. It might still not be a very large probability at all, though. Okay, that's decent. About 9.1%. Good. My example worked. So there's the example. What's the average? On average, how many tests? Right? On average, how many tests do we need to find the first defective product? Well, that's going to be, remember, 1 over p. So that's 1 over 0.001. And so 1 divided by 0.001, 1,000. So on average, it will take us about 1,000 tests to find the first defective product. right? So there's sort of the geometric distribution in use. That's pretty much it for geometric distributions. So we have pretty much covered the distributions we set out to cover in terms of discrete, right? Remember that all of these are still discrete distributions, even in this example, or I can't have 95.6 tests, right? I can't do that, right? It's discrete. It's still only a certain amount of outcomes. Next unit, we're going to start talking about continuous, and it's going to still take a lot of the same ideas, a lot of the PDF, CDF type ideas, and some of those diagrams into play. For this, because we don't have a book, this isn't in the book, there is a homework sheet on Schoology, and that's it for me for today, and I will see you next time. All right.